This is data plots and graphs. Oh my, this was originally done, I think, 3 years ago, and it didn't get recorded. So we're doing this one again. I think it's a pretty good one. Let's see what you all think about it. By way of introduction, a lot of what is in this presentation comes from How to Lie with Statistics, which was written by Darrell Huff in 1954. He was actually not a statistician, which I think is important. He was a journalist, and this book was used as a textbook and was a bestseller and translated into all kinds of different languages and such. But every day we are surrounded by visual data. And Huff says, statistics aren't evil in and of themselves, but they can be dangerous in the wrong hands. So we always want to ask, who is showing me this data and why? Because over 80% of the information our brains take in is visual. We are wired to look for patterns, color cues, and trends. And we also, as human beings, tend to trust what we see, especially if it looks polished or professional. But just because something looks clear doesn't mean it's accurate or complete, right? Visualizations are supposed to inform, but they can also mislead. And sometimes this happens by accident, but sometimes it happens on purpose. And so you often see folks say, well, the numbers don't lie, but do they? So numbers in themselves may not lie. The numbers are what they are, but how they are visually presented can be very misleading. Statistics is the interpretation of data to uncover patterns, meaning, and make inferences about how we ought to make decisions, right? But it can be interpreted selectively, and it certainly can be visualized in ways that shape or distort what we see. So this tends to happen more often in business and politics, right, than medicine. But oftentimes scientists, researchers, clinicians, they set out to do a research project, but they don't involve a statistician at the start of that research project. So things may not be designed right. So they'll collect their data. Then when they go to the statistician and say, this is what I want to do, the statistician will say, well, you can't do that with that data, but they'll want to do it anyway, right? So we all need to be able to recognize when data is misrepresented, whether or not that's intentional or accidental. It does happen. Okay, so when I did my MPH at UAB, I had the amazing Dr. Austin for biostatistics, and she had a huge section on how to make a good graph. And she was very enthusiastic about it and very good. And so for her checklist included the following elements. You got to have a descriptive title. You got to have labels on the axes. You got to have clear category labels. You got to have a legend, and you got to say where the data came from. And she was hard on this now. Do not use 3D. Do not use 3D. Here's what she said. She said, do not use 3D. It's ridiculous. It never prints clearly. It doesn't look good. It's misleading. It makes it look as if we have three-dimensional data when in fact we really don't. We're looking at two-dimensional data. So there's no reason to use 3D when we create graphs, and it's often used to misrepresent data. So let's look at that. Oops, there we go. So we've got some 3D madness here. And so this is a painting that shows, this is a two-dimensional painting that looks 3D. And the boy is coming out of the painting and he looks like he's coming at you, right? Our brains, when it's 3D like this on a two-dimensional surface, we struggle to judge volume, angle, and depth, right? So a slice or a bar may look larger because it's closer to the viewer, not because it actually represents a larger value. So we see this in the pie chart on the right. The green 20% or the teal pops out more. It looks bigger than the two-dimensional, right? And then the same thing with the graphs, bar chart on the bottom right. Those graphs look different. The blue and the orange look much closer together 3D than they do on the 2D. And you see on the 3D, the green bar, the category C, doesn't quite touch the top 50, but on the 2D it does. So 3D is kind of one of those red flags you want to look for. 3D can also do occlusion. So elements can be blocked or obscured from others depending on the angle. This gets worse if the chart is really dense, where important values could even be completely buried. And in our minds, what's behind is less important, right? If it's farther away, it's not as important as if it was close up. 3D adds to the cognitive load. It's complexity without clarity. Shadows, angles, perspectives all make the charts harder to read. And then there's chart junk, right? Like you see the labels on that bottom right, they don't float, they're floating off center. They float awkwardly. They are misaligned. And the more you have, the more 3D, the weirder it gets. Like in this image right here, right? It's really hard to see the labels, how they match up, and how the bars are angled and skewed, right? So the visual wow, like, wow, you must be smart, you made a 3D chart, it really adds nothing to the message, and it can actually take away from it. This is one of my favorites. This is a flaw of averages, and I always use this cartoon where the statistician drowns crossing a river that is only 3 feet deep on average, right? So in this simple data set, the mode and the median, right? Mode is a number that occurs most frequently. The median is the middle value when numbers are in order, right? These both suggest a typical value of 1. But when we average it, we have an outlier up there. That 20 makes the average or the mean 2.9. So 3 is a good jump away from 1. So it misleads what is actually the actual experience of the people, right? We say averages can hide more than they reveal, especially when there are outliers involved. So I've got another example of that for you. So here, if we have a small company with 10 employees and we have their annual salaries in thousands, right? So if we look at the median, the middle two salaries are 35 and 36. So if we add those together and divide by 2, because that's what you do if it's an odd number, then, or an even number, then you divide by 2, you get $35,000. The mode, it occurs the most often, is 30, right? But if we average that out, it makes it look like the average salary is $80,300, right? So the real experience for people is the salary is about $30,000. The mean is wildly misleading here. That's probably the CEO, the 80,000, right? That's probably the CEO, probably more than that. But you can see how the mean is not actually representative of that data. So whenever they say, here's the average, it's like, yeah, but what's the median and the mode? You want to see all those numbers represented. And here's another good example of this misleading. Generally, barcodes are encode quantity by length. Our brains interpret, right, a longer bar as meaning more. So even a small difference can look bigger if that y-axis does not start at 0. So this is known as a truncated graph, and it exaggerates the differences that aren't meaningful. And you see this a lot in the news. They will truncate a graph where it does not start with 0. Now, there's always an exception. There's always an exception. There may be a reason. But if it doesn't begin with 0, you always want to ask yourself, why did they not begin with 0? So we say a clear, honest chart should always have the y-axis baseline starting at 0. So you can see on this one, the first one is a more accurate representation. We're just talking about 5 points, right? Group A, the difference between Group A and Group B is 5 points. On the left, that doesn't look so what, right? But if you represent that data the same way on the right with a truncated graph, then that looks much more significant when it's not. Okay, so I've got a real world example for you of this one. So this is a real example. This came from Germany's Economic Development Agency on their webpage promoting the German labor market. And they're claiming that German workers are more motivated and work more hours than any workers in other EU countries. But look, the x-axis starts at 36. Okay, so now if we fix that graph, it's not so dramatic, is it? It looks like, wow, Germany really outperforms France, but do they? Not really, not when you have it 0 there. So that's pretty wild. I always look for 0. Another, this is one of the ones that people consider the most serious offense, is cherry picking. So that's picking the data that only supports your claim and ignoring the rest. Right? It's one of the most harmful ways to mislead with statistics because you're giving the illusion of evidence while hiding the full picture. This happens when people want to highlight results that make their case, right? And we see this a lot in the news, well, forever. While leaving out, you leave out the inconvenient stuff or the contradictory stuff. Of course, we already said that, in public debate and political messaging, you see this a lot because you can present real data, but you only show a carefully filtered slice. So using the same data, one group can show crime increasing in a single year, where another group can use the exact same data and highlight, a decade-long decline. Both are real data, but they paint a very different picture because the data used to visualize the result is cherry-picked for the result that this group or person wants. It is used to manipulate perception. And it can be accidental, especially when a researcher or presenter is not aware of selection bias or has a really narrow focus. Another red flag you should look out for is a irregular scale or unequal intervals, right? A chart scale should be even and proportional to the data, especially along the x-axis. So when we're showing change over time. So in the brown graphic, you can see there on the far left, we start at 0 and then we've got this expanded space to 10, and then we just go 10, 20, 30. So we've got some not even stuff going on there on the far left. That's a red flag. Okay. For the other one, in the blue chart, everything is spaced nicely. Everything is the way it should be, right? Each category, year group, evenly spaced, accurately reflects the timeline or progression. Great. The red chart is the same data, but the spacing of the bars is irregular. Some years are closer together than others, right? So we've got this gap, and you can see it does something in your brain. It's like that makes those last 2 years look more significant. The bars are also a little narrower, right? Makes them look taller. So you want to be sure that both axes are nice and even. There's nothing irregular in the intervals on either axis. This is one of my favorites too. I like this. I love me a good infographic now. I'm a fan, but scale matters, right? So here we're looking at volume, okay? So we're trying to say that we have more elephants than giraffes, but we have more pandas than elephants or giraffes. But those little infographics those little animals need to be all the same size. Because if you look at the one on the left, the bigger elephants, because elephants are big, right? But the bigger elephants make it look like there are more elephants than pandas when there's really not, right? So size must match proportion. That small change in size can suggest a much bigger difference than the data supports, right? Our brain just naturally interprets larger images as more, even if that difference is only symbolic. Here's another thing you got to watch out. Oh, the pie charts. Everybody loves a pie chart, but they can easily be distorted for perception, right? Even if the data is the same. So on the left, all the slices are equal and fairly representative. But on the right, we've got the cherries popped out. They call it an exploded out wedge, right? So that draws your eye to that, makes it feel more important, even though it's 25%, just like the other four or other three, right? And it looks bigger because it's popped out. So if a pie chart is not a solid pie, right, that's a problem. The slices are similar in slices are similar in size or hard to visually compare. If labels are missing or unclear, that's a bad thing. If one slice is pulled out like we have there, that's not good. If 3D distorts the whole thing. And this is a big thing. If the total does not equal 100, then that data does not need to be in a pie chart. A pie chart is supposed to equal 100, not more than 100. So I'll show you a hot mess. This is an actual thing that was in the British paper, right? And they're saying that mushrooms are Britain's most liked pizza topping. But look at this hot mess. First of all, we've got more than one variable on each slice of pizza. So they've got bacon and sweet corn and peppers on one whole slice. So how did they even, right? So, but this is just a hot mess, and it adds up way, way more than 100. So this kind of also reflects back onto our pizza chart when there are too many variables at once, right? So cramming too many things in a graphic is confusing, and you end up overwhelming people. So one of the things to look out for are dual axes with different scales, right? If you want one chart to have one scale, you don't want to have two things on a chart that have different scales. That's just confusing. And it can make you think that things are connected. Things look aligned, but the scales tell a different story. Too many colors, there's no visual hierarchy. Everything starts to blend together, nothing stands out. Too many data in a series. The more lines or bars you add, the harder it is to see what matters, right? A chart is not supposed to be a spreadsheet. Mixing chart types. So you've all seen a chart that has bars, lines, and bubbles in one space. You don't want to mix a chart. Keep it simple. All right. And now tiny and unreadable labels, right? That's especially common in dashboards or exported charts. Even if your viewer has to squint or guess, they'll give up before they figure it out, right? And in this little example I have here on the slide, what do those things even have to do with each other? So keep it simple. Keep it simple. Another thing to watch out for are colors. There's a whole field of psychology and emotional things that go along with color. It's much more than decoration, right? Color is a powerful tool that you can use for a variety of good and bad. Used poorly, it can distort your perception of things. It can stir emotions or just confuse people. Our brains are naturally wired to respond emotionally to color. So red is a primal, right? Red, danger, urgency, alarm. And then green tends to promote safety, positivity, and growth. Blue tends to calm people and bring out feelings of trust and neutrality. So if you have a chart that shows rising numbers in bright red, even if, it's just something silly like we have more grapes in the store than we do strawberries today. Red can cause people to have an emotional response of panic is urgent. Oh my gosh, right? Green used for a negative trend, and the example I have is rising pollution. That can make it seem less concerning than it is, just psychologically. Using a whole bunch of colors in a single chart, like a pie chart. We've all seen one of those charts that just, they've gone through the whole spectrum and now we've got all the colors of the rainbow and all their different hues, and it's just too much. You have all those colors in there. It's obscuring patterns. It's creating visual noise. And it discourages people from taking a close analysis of things. And plus, about 1 in 12 men and 1 in 200 women have some sort of color blindness, right? Often red, green. So if your chart uses only color to convey meaning, especially red versus green, you exclude part of your audience. And you don't want to do that. That's not nice. This is also a good one. 200% increase. Who doesn't want that? That must be a great headache reliever right there. Great 200% increase in efficacy, but it was just, went from 1 to 3. Whoops. So percentages are attention grabbing, but if you don't have that baseline number, you could be being tricked there. Without context, percentages can make these small changes seem huge, right? It hides how many people were actually involved, and it encourages the assumption that the change is meaningful or widespread. Huff says a headline may scream 50% of the patients improved, but then you read down in the fine print, it's like only 6 people were in the study. So 50%, 50% sounds huge. That's amazing. But then it's only 3 people, right? So you always say percentage of what? Always ask what percentage of what? And then lastly, these 2 things, a small sample size. If you have a small sample size, like kind of what we were just talking about, right? That increases the chance of random error or something weird going on. I love that quote from Huff that says, with a small enough sample, anything can happen. And then he uses that cool example of 3 out of 4 dentists recommend the brand of toothpaste. He says that tells you practically nothing. It doesn't tell you much. And like, especially if those 4 dentists were picked because they already like the product. And then finally, if you have not ever seen this wonderful just piece of loveliness in the world, the Spurious Correlations by Tyler Vigen, correlation is not causation, right? And I love the examples he has on his website. Like this one is annual U.S. household spending on fresh fruit correlates with Canadian National Railway Company stock price. And he's just got a whole bunch of those spurious correlations on his website. So if you have never seen his website, go there right after this and take a look. He's got some really nice examples that you can use in your classes when you're trying to explain this to folks. And so that's the last bit of that. If anybody has any questions or anything, let me know. I got the chat open, and I've also got the feedback slide here and what's next.